the main point perhaps is to understand or explore for Laplace equation. Now we have the mixed boundary condition for x equals 0. I have 0. X equals L. I have 0. So maybe if we just like to think of three-dimensional Laplace equation is you want to model something mathematically, and when you model, you want to put boundary condition, and if you don't know how to choose the boundary condition, then you will not be able to model it. So that's the purpose of analyzing these problems. Okay. So if we look at the solution, I just jumped into, you can just jump into the solution. So by looking at Laplace equation, you see that this is the eigen decomposition. I have a h phi. It does not have to be. You can take f g. Sometimes I'm looking at f g. H phi doesn't matter. And for Laplace equation, this one, what value of lambda to choose for? It depends on the boundary condition. So you look at the boundary condition is Dirichlet boundary condition in x direction. So x direction component, if you set an eigenvalue problem that has eigenfunctions, either sines or cosines, if you can figure out, by looking at boundary condition, it should looks like the sines. And then if I choose, if I put a minus sign here and put lambda plus, then definitely for h, I get a eigenvalue problem that has a solution sign. So that is something thinking under the hood to set this up. Okay, right. So then you look at here the y component. So y component, the boundary condition is now 2 term. So the boundary condition is 2 term, and by looking at that, if you look at here, the characteristic roots are now positive real numbers and negative real numbers. One is square root of lambda, one is minus square root of lambda. So you have exponential solution. So you can form the solution e to the power something positive, e to the power something negative, or you combine them together just to remember. I know some of you might be confused. Cos hyperbolic y would be e to the power x plus e to the power minus x divided by 2. Sin hyperbolic y would perhaps be e to the power x minus e to the power minus x divided by 2, and so on. Okay, so if you write that, then you can have this sin hyperbolic. So one will be sin hyperbolic, one will be cos hyperbolic, and make a linear combination, and then apply this boundary condition. So you differentiate and then form this. Okay, so you have this relationship between two coefficients. Remember, I have a single non-derivative term plus a derivative term. Looks like two term equals. So sometimes we get confused. I should be able to find the coefficients, but no, because this is a single boundary condition. I have two coefficients, C1 and C2. So I need two conditions. So from this condition, I can only find one coefficient, and the other condition is given in a generic function. So I cannot use that to determine those coefficients here. So you end up with an arbitrary constant. And this is one example in Laplace equation. In heat equation, in wave equation, or in other equations, we may have an arbitrary constant giving us a family of solutions. So that's the main point to look at instead of just solving this problem. How get the concept, how we are getting a familiar solution based on an arbitrary constant. One constant we cannot determine. Well, we can just write down the solution now. If I substitute back those coefficients here, so I can say, okay, so I have a eigenfunction phi n, and I have C1, and I have here okay. So once you have that, you put that back into here, and you see that I have h times phi, and I'm thinking doesn't have to be C1, because once you choose an eigenfunction phi and C1 is just an arbitrary notation, so you can choose any symbol. So let's say a good familiar symbol an, and then you substitute h and phi, and then if you look at the boundary condition, either right here or right there, this becomes a series, and we can use the orthogonality of sign. So in this series, we will be thinking that maybe everything here is a coefficient. That's something to be careful to identify the series. So let's say everything here is an. So if you have just memorized sines and cosines, you multiply and then integrate. Once you see sine hyperbolic and cos hyperbolic, you might be multiplying with sine hyperbolic and multiply with cos hyperbolic and trying to do something. So because those are not our orthogonal bases. So they are kind of here coming to the expansion coefficient. Also, they are not functions. They're evaluated only at some point. So this part is just a constant. And then we use orthogonality to find the constant. Well, so this is a bit messy, so we can say this is number 1, this is number 2. So 1 gives the solution, where 2 gives the coefficient. Okay. So maybe we can move on to a second example, which is wave equation. And I mentioned the other day that we will have 2 branch of solution. It's like wave equation always have 2 branch of solution, one right moving characteristic and the other left moving characteristics. So even if we are using this separable variable technique, we will have 2 branches. And for this exercise, I have given very simple boundary condition. Well, initial condition, I think we need to specify some boundary condition too. So I will add some boundary condition. 0 y equals 0, u l y equals 0, and I will add du dy x 0 equals 0, du dy x h equals 0. So the other point is that one boundary condition in x is Dirichlet, and the other boundary condition in y is Neumann boundary condition or derivative condition. So which gives you a hint that in x component, the eigenfunctions will be sines, and in the y component, eigenfunctions will be cosines. So that we have in mind before starting the solution, and then I will not write down in details. So we'll start with the separation of variables, say phi of x, y. We could, or we could say, sorry, we could take the product solution h of t, f of x, d of y. So both way it works. So we'll first end up with a equation minus, I think I will write plus on this side, c square lambda h equals 0, and lambda positive. Okay, from this quantity, which is ux y0, that will be h of 0 phi x y equals 0, implies h of 0 equals 0. So it is a like Laplace equation. It is a second order equation, but for t variable, I have one boundary condition. Other boundary condition has an arbitrary function. So similarly, in Laplace equation in y direction, I had one boundary condition evaluated, the other boundary condition was arbitrary. So we'll go the same way. So this one will have now a solution of the form lambda t plus b, doesn't matter uppercase or lowercase, as long as sine c square root of lambda t. Okay, so then we will have an eigenvalue problem. Once we decompose that, I will have fxx plus mu f equals 0, f of 0, 0, f of L equals 0. And I will have G. I'm skipping step because I have already discussed those steps earlier. So that is the same thing. Lambda minus mu, G equals 0. And this time, sorry, that is a typo. It should be y. G of y 0 equals 0. G of y h equals 0. So those we can solve. We have learned how to solve them. So let's say if we write down the solution, maybe I can just say follow previous lectures. Phi of n x y will be sine of n pi x over L cos of n pi y over h. In fact, is because this is an eigenvalue problem. We have already seen we understand that the boundary condition, because we are not completely analyzing that. We are saying this one is a second order eigenvalue problem, and because of the Dirichlet boundary condition, I have sines, I have cosines. So as long as we understand that, it is not necessary to show this part of the work. You can skip that part. So then I have with this, we have already figured out in previous lecture that will be n pi over L square plus m pi over L over h square. Okay. So we can now write the solution u x y t. Solution u x y t would be sum over, say, m going from 0 to infinity, and you might think that why not 1 is because we have cosine. So when we have a cosine term, we start from 0. For sine term, we just ignore 0, is because sine 0 is 0. And that will be a coefficient, and that is nm, and then sine n pi x over L. Maybe I can make things little clear. And this one is my f of x cos m pi y over h, which is g of x, when I'm looking for the product solution. And I will have sine c lambda n m t. Because for h part, I have two branch of the solution. One is gone is because I have one boundary condition. So I can take just sine, okay? And then we follow so I didn't completely have shown the work. I have some intention in mind, so I want you to work it out yourself. That instead of those are longer questions, right? So instead of doing many examples, take one and see if you understand one. Then you can figure out the rest. Okay. So I have done that Laplace equation and that wave equation. That's fine. So let's start with something that earlier at the beginning I said, what value of f or the boundary condition, how do you choose the boundary condition in order to be able to solve the problem? So said in another way, are there any condition on the boundary condition on the boundary conditions in order to have unique solution? So that type of technique we want to understand. And in order to do that, we will be looking for orthogonality. So maybe I can just put a section title, Green's identity. Okay. So let's first look at multidimensional orthogonality or inner product. Inner product in Rn. So take two function f g, they are from Rn to Rn. So f of x R1, f of xy if we are in R2, f of xyz if we are in R3. In physical world, we are always in two-dimensional space. In numerical or data world, we are in n-dimensional space. So everything, when we say that a function is from is defined in Rn, n-dimensional space, everything is covered. So the inner product would be given by now. We have an n-dimensional domain, so I cannot go from A to B or 0 to L, and my function f is a function of n independent variable, and then I will use some weight as in the one-dimensional case and dB. So that is the inner product. I will use here star for clarity. So I will say here G star is complex conjugate. So it covers if we have to deal with complex functions. Generally in PDE course we deal with real functions, real valued functions. So in real valued function, G star will just be G. Okay, so that's our starting point, and then we can define orthogonality in multidimensional space. So if inner product is 0 in Rn, then f and G are orthogonal. The dot product is assume the dot product. So A dot B equals 0. So they are perpendicular. Okay. So if I have those ingredients, and maybe just for clarity, let's define. I have not said what is the symbol omega means. So omega will be a subset of Rn connected, or maybe you can say simply connected and closed. If you look at this bucket, so this is a domain omega, it is open. If I close the door, this room is a domain omega, it is closed. And that is where always we have confusion when we look at the domain. So closed domain and open domain. Okay. Boundary of omega. So those are the notation we will be using continuously. So let's recall divergence theorem. So any of you can tell me what is divergence theorem? I forgot it. Okay. So divergence theorem is just a vector field diverging. A vector field diverging. So that means you take a domain omega. It will be diverging from the domain. So you look at the boundary. How much is going out of the boundary? So that's very easy. We say, okay, f is from Rn to Rn. In vector calculus, we did not say that way. And we say be a vector field. We don't have to say it is a vector field. If f is defined from Rn to Rn, so its input is n-dimensional, output is n-dimensional. So output must be a vector. And if it is taken from many points from Rn, so it will give many points, maybe some of them superimposed, but it will give many points. So it is a field. So divergence theorem states that if I integrate divergence of f on that domain, the vector calculus I use three integrals, three-dimensional. Here, I don't want to use n-dimensional symbol here. So one symbol omega is n-dimensional. Is again on the boundary delta omega f dot n hat ds, and n hat is the outward normal, n hat is unit outward normal at every point r of delta omega. So delta omega is a surface and ds is an elementary It's nice mathematics, not complicated. Not complicated because we are not going to do any functional analysis or real analysis. So that is why it will not be complicated. It will stay easy. Okay. So that's the divergence theorem. So let's pretend we are green. Of course, we are green. So we explore some cases. We are green. I don't mean green party, so don't bring politics. So the Green's identity are like scientist green. Okay. So F equals grad U. F is a vector field. So I can have a scalar. U is a scalar. So will be U from Rn to R. U takes n-dimensional input and gives you a number. Okay. Delta is d dx1 comma d dx2 d dxn is gradient. Is gradient. Okay. So now we apply divergence theorem. We apply divergence theorem, divergence of f omega, that will be, maybe I can write dB divergence of gradient of u dB. So that can be written as, so for the left hand side, nebula square u dB, and now on the right hand side will be delta omega f dot n hat ds, which is delta omega gradient of u dot n hat ds. If I write down the final result, then that will be omega nebula square u dB dB equals delta omega gradient of u dot n hat ds. So that tells me the Laplacian of a scalar function. I did not say what is the function u. I started with a function. Any scalar function you can take the gradient, make a vector field, you can apply divergence theorem. So it can be any scalar function. So if you take the second derivative of the scalar function and make the Laplacian, integrate it, it is coming through the boundary. So it states that if we have Laplace equation then so that's a constraint on the boundary condition for Laplace equation. So in order for solution of Laplace equation to exist, we would need that condition to satisfy. So let's add that result in a little different way. So let's say I have a Poisson equation instead of Laplace equation, and this is multidimensional. It could be one-dimensional, two-dimensional, it doesn't matter, written in a multidimensional way. And then we have the boundary condition gradient of u dot n hat equals let's say g of x or h of x on delta omega. Okay, so then we have to choose f and g such that or also that implies maximum principle. We should be able to figure out that, but at this point, the main point is the condition. So if we go back to the Laplace equation that we discussed today, we had 0, 0, some condition 0, and f. So the necessary condition for f would be you integrate f. Well, so now f has to be something related to the derivative of the solution. F should be somehow related to the derivative of the solution. and that has to vanish for Laplace equation. Okay. Well, choosing F, you are a professor now, and then you are giving the assignment. You have to give it in a way. So I have to choose it. So if I formulate the problem, I have to give you the problem in a way that F and G satisfy that condition. Or you are modeling something and then you are solving an equation, you have to check that this is the condition. Yeah. Otherwise, solution will not exist. Clear? Yeah. Okay, so maybe I have one thing here. So this one will be GDS. Okay, so that is the necessary condition. So let's look at Green's identity. So, and also this is a sorry, I think okay, there is a typo. Thank you. It's not G, is H. Because I've written here H. So H is somehow related to the derivative of the function for a Neumann boundary condition. So I have to choose H. In a way, my expected solution should have the gradient something given. And then if you integrate that over the surface, it should be 0. So which means it is somehow satisfying the divergence theorem. We have heat inside a domain. So we will have heat gradient, which will be the vector field. And that vector field passing out of the domain, if I integrate that, that should be 0. So only then we can define a heat equation in a multidimensional box. Okay, so let's try to be Green and find Green's identity, maybe the first identity, let's say first identity. So I take a vector field F, I take a scalar field and then multiply with another gradient. This is something Green's thought at that time. If he did not do it until today, maybe I would have done that, and instead of it would have been Joule theorem instead of Green's theorem, or one of you could have done that, right? Very simple idea. And then we apply the divergence theorem. So apply divergence theorem, you say, okay, divergence theorem would be divergence of U grad B dB equals U grad B dot n hat ds. And then we want to evaluate the term on the left hand side. And how do we evaluate term on the left hand side? I will not say, okay, so I have the vector calculus table. Even if I teach vector calculus, I don't say memorize the table. I say we just use our basic knowledge. So this divergence is a differential operator. It is operating on U times gradient of U. So it is a product rule. So we will be simply thinking of product rule. So let's recall product rule. Sorry, U. B prime. So if I apply this to divergence, U get B, so that would be U get B plus U. So I have to fix something, it's because it's a divergence operator. So it changes its nature where it is operating. So here I am operating nebula with U. U is a scalar, it's a gradient. But the next term is gradient. So then the product will be here a dot product. We'll have a dot product. And then I see here I have U, which is scalar. This is a gradient operating on a gradient, and gradient is a vector. So that will be a dot product. So it's the same as product rule, but knowing what is this nebula operator, or what is this gradient operator, or what is the divergence operator. That's all the difference. And this is one of the purpose of this type of discussion here, to make us more familiar with those operators, so we can understand PDE better. Okay. Now we can see here. You can see gradient of U dot gradient of B plus U, and this one we can write nebula square B dB equals n hat ds. I'll put a box. And we don't memorize that. What we look at here is the trick, is the idea. We have the divergence theorem, and in the first identity, we look for a scalar multiplication with a gradient, U grad B. So a scalar, we have two scalar, and we take gradient of one, multiply with the other one, and then apply divergence theorem, and then we get the Green's identity, first identity. So Green's, I will not discuss the third one, don't worry. There is a third one, Green's second identity. Will stop there. Identity. So we take the first identity, start with the first one. Can you tell me what I can do now? I don't know anything. You don't know anything. I don't know anything. What can I do? Go ahead. Yeah, so that means you are pretending you are a knowledgeable person. If you are just a kid playing with those things, what you can do? You will just play like a kid. So here is your toy, here is a toy. You just take this one there, this one there. So Green only did that. He just played like a toy. So you just change U with V. So if I do that, gradient of B dot, gradient of U plus B nebulous square of U dB is uppercase B. Okay, so now you have a next move of your game. If you switch again, then you go back. So that is not your next move. Now what could be this time a next move? I can do much. The easiest thing I can do either add or subtract. If we add, we will accumulate. If we subtract, we will try to reduce that. So we'll subtract. And you see, this one, grad U dot grad B and grad B dot grad U is the same. If we subtract, that will cancel. This is scalar product. Grad U dot grad B is a scalar multiplication of two vectors. A dot B, B dot A is the same thing. So if I subtract, this part will be 0 plus U m plus square V minus V m plus square U dV equals. So let me just write down first this part without 0. U nebulous square V nebulous square U dV U grad V minus okay. So that was earlier, so I did not have chat open, so I did not see it. So we'll look into it later on. And V grad U dot n hat ds.